our afternoon session, and Venugopalan will talk about how the topology of QCD vacuum influences the proton spin.
Yeah, thank you very much. So I think this is a slight shift in the discussion so far. That's my knowledge. This is the only talk focusing on the high energy perspective in terms of understanding the role of topology. I don't know if Rob's going to say something along those lines, but anyway, so here's wait, does it work?
Just touch the screen.
I think I know what's going on. Oh, that's right. Okay, great. Okay, good. So this is work in collaboration with Andre Tarasov, who's at North Carolina State University and CFNS at Stony Brook. It's based on two papers that we wrote not too long ago. So I'm going to introduce you to a problem in physics called the proton spin puzzle, and it's something that's been around for quite some time. And I'm going to talk about what anomalies have to do with this, and I'm going to do this within the framework of our wordline formalism of QCD. And then I'm going to say how there's some very interesting non-perturbative chiral physics that results, in particular a Goldberg-Triemann relation that's relevant to this problem. And then I'm going to talk about how anomaly cancellation and topological screening occur and influence the proton spin. And finally, I'll talk about what happens at really high energies in this problem, that where the physics can be described by an axion-like effective action. In particular, this exciting possibility that you can look for evidence for topological sphaleron conditions, which diffuse the spin of the polarized protons. Okay, so that's my introduction. So what we know is that the proton is a complex many-body system, and so the one half of its proton spin, some many-body composite of the spins of the quarks, the gluons, and their angular momenta. In particular, there's a famous sum rule called the Jaffe-Manor sum rule, which is a particular decomposition of this in this way. And that's not going to be my focus in this talk at all. So you can actually extract information about the quark helicity of the proton independently from experiments. And that's what I'm going to be focusing on. And there were experiments done, deeply inelastic scattering experiments that were done of polarized protons, which now show that these quarks carry only about 30% of the proton spin. The early experiments actually showed that these were much lower. In fact, the earliest experiments seem to suggest that it was consistent with zero. And that was dubbed the spin crisis. And so when I refer to the spin puzzle, I'm really referring to this particular issue. And it was interesting because it revealed a dramatic failure of the relativistic quark model. Picture where the spin is carried by relativistic constituent quarks. In particular, a specific prediction called the Ellis-Jaffe sum rule said that the isosinglet axial vector current, which as I will discuss is relevant for the quark helicity, is equal to the isosinglet axial vector current. The iso-octet as axial vector current, and that can be determined from hyperon decays. And on the basis of that, an sg3 flavor, you would argue that it should be contain about 60% of the proton spin. So the current experiments suggest that only 30% is carried by quarks. So this is still a significant failure of this quark model picture. And the question is, why is that? Okay. Now, this observation, fixed target experiments, led to a program at the Relativistic Heavy Ion Collider at Brookhaven, where they did very high energy polarized proton-proton collisions at energies up to 500 GeV. It's the only polarized proton-proton collider in the world. And so the idea was to then extract, say, the spins of gluons from this end, and there were some suggestions that this could be compensated significantly by the spins of the gluons. And so here, this is not a very good plot, I apologize. So here's the data on the extraction of the gluon spin. So that's the integral over all values of 0, k, and x from some value of 0.05 to 1 on the x-axis, and that's what Rick can access. That's the highest energy or lowest x that's accessible by Rick. And on the y-axis is the integral from 0.05 to 1, which will be accessed in the future, as I'll discuss. And so the red, so this data here show this light green curve is the situation before Rick was turned on in doing these polarized BP collisions for the gluon polarization. And so this is the current status, where you see that there's evidence for a positive gluon polarization, but there's still a very significant uncertainty which needs to be addressed.
Raju,
Yeah.
are you going to comment on the fact that these are all scale-dependent questions?
Yes.
Right, that this is not really,
Of course.
what we call a direct physical
Yeah.
observable.
Well, so let me well, so the left-hand side is scale invariant, but all the different the right-hand side, and so that's actually my great. So I'll come to that.
Is there any some of these parts are none of this is still not invariant? None
No,
of the
no, they're all
they
scale.
are all, but
All scale invariant. I mean, they are, turns out, actually weakly scale dependent. But they are scale dependent. And so come to that. So an exciting development is the possibility now of doing polarized electron-proton collisions at the Electron-Ion Collider in Brookhaven. So since many of you in the audience may not be familiar with this, so RIC is a relativistic heavy ion collider where you have two beams of nuclei or polarized protons which circulate and collide. And so the Electron-Ion Collider, you move one of those beams and replace that by an electron ring instead. And so you can have a collider experiment. It will be the only collider experiment in the United States, and it's built, which will collide polarized protons up to 275 GeV. That's the energies of polarized protons, and nuclei up to 0A of that. So roughly 100 GeV or so, maximally, and electron beams up to 18 GeV. And so that would be a center of mass energy between 20 to 140 GeV. Okay, so quite high energies, somewhat lower than that of the Hera collider. But what the EIC has going for it is that it can do polarized protons and nuclei. And also the design luminosities are over 1,000 times that of the Hera collider. So you can really do a wide range of differential studies for a number of processes. So here's the slide, which hopefully will address Larry's point, is that what you do in practice is to extract the components of the proton spin, in particular the quark helicity, is you look for asymmetries in the scattering. So you have a polarized electron scattering with polarized proton, as shown here, these arrows. And you look at asymmetry in the cross section for the scattering between the polarization of the proton in one direction and the other relative to that of its polarized photon. And so this asymmetry is proportional to something called the G1 structure function. And that is, so that's a polarized structure function, in analogy to the unpolarized structure functions. And it's in general a function of x, so this is Bjorkane x, which you can think of roughly as the fraction of the momentum of the proton that's carried by a parton, a quark and a gluon inside the proton. And so it's a function of x and q squared, where q squared is the resolution of the probe. And so this, this quark helicity that I mentioned previously, the spin of the proton, is the first moment of G1. Roughly speaking, it's actually the isosinglet part of G1, whose first moment is this quark helicity. And so what's shown here on this plot is G1 is a function of q squared for a wide range of these x values. So going to smaller x means going to higher and higher energies. Okay. So q squared over the central mass energy squared is roughly what x is. And you see, here's the world data on polarized deep elastic scattering. Okay? So everything that we know at larger q squared and small x is from extrapolations based on perturbative QCD. And that's what these yellow bands denote. Okay? So as you see, as you go to smaller values of x and larger q squareds, the uncertainties grow because you have only limited data, which is providing you your initial conditions. So because of that uncertainty, these uncertainties grow as you go to smaller values of x and high q squared. And in fact, if you believe, as people who do perturbative QCD do, that the first moment that the logarithmic derivative of G1 is proportional to the gluon polarization, so that's delta G, then the yellow band here shows you the uncertainty corresponding to these extrapolations in this polarized gluon distribution as a function of x. And you see it's very large. And now what the EIC is going to do is it's going to give you data in all these little points here. So it's going to shrink those error bars down to close to zero. Okay, so you're going to have data here. So this is mock data that's shown here. But as a result, the uncertainty in this gluon distribution is going to shrink to this very small red band. So,
sorry, can I ask on the
Yeah, sure.
previous slide?
Yeah.
In the plot on the left, how much of that is going to be covered once the EIC turns on?
all of it.
All of it.
Yeah, that's the point. So these are the sort of projected data points. So these yellow uncertainties will just shrink to
I see, that's the
zero.
I see. Thank you.
And so you can actually look at this plot in a different way, as a function of x now, for a fixed q squared. And so these are these are different EIC energies up to the highest EIC energies. And so you're going to have data points up to here. And based on current extrapolations of available data, you can have this G1 either explode in one direction or explode in the other. Is completely unconstrained. And the sign of G1 is not fixed to be positive because it's an asymmetry. And so when you have this data, it's also going to constrain this extrapolation down to further x. And so to just summarize all of this in one plot, if you look at the integrated gluon polarization on the y-axis versus that of the quark polarization on the x-axis, up to the lowest EIC values of x, the current uncertainties in the data in both will shrink to this little yellow blob here. So this is really going to dramatically improve our understanding of the polarizations of quarks and gluons inside the proton. Yeah.
How constrained theoretically is the shape of G1 in the sense that could it wiggle? Could you collect some data? It looks like it goes down, but actually turn right back around. Is that possible? Like, is there some theoretical prejudice here?
Yeah, so I think so there are theoretical prejudice from regular physics and also from what I'm going to talk about actually. So what I'm going to talk about is actually how, what are the possible shapes that you could have and what they mean actually. And so what I'm going to argue to you to give you a preview is that from the shape you can learn something about sphaleron conditions. Okay.
Okay, very good.
Yeah, so so that's kind of my punchline.
Okay, sorry. Okay, good.
By measuring this, you can learn something about that. So, the way you do it in perturbative QCs, you have some initial data, some initial scale in Q squared at all possible x's, and that's based on, say, Regge theory or some prejudice, some model that you have, and then you extrapolate this to higher values of Q squared. Now, in the Parton model, what is our interpretation of G1? In the Parton model, G1 is the sum of the charge squares in different flavors times what certainly is delta QF plus delta QFR, which is the difference between the Parton distribution of proton along its direction or anti-aligned to its direction. So it's the number of partons in a polarized proton that are aligned in the direction of the proton or anti-aligned to it. Okay, so it's a difference. So it's really kind of the quark helicity in the polarized proton that's proportional to G1. Now, this is, of course, summed over the different quark flavors, so it's not democratic. And so what I'm going to be talking about is the isosinglet component, which is just the democratic sum of all the quark flavors. So you can separate the two out, this isosinglet and the non-singlet components. Now, you don't have to go to a Parton model interpretation. In general, you can just measure the cross-section. So you can measure the anti-symmetric part of the hadron tensor. And a particular projection of that is what G1 is. So you don't necessarily have to go to a Parton model interpretation of the data. You can just directly measure the cross-section and extract G1 or calculate it in some way. So this is what I was saying, is that the first moment in X of G1 can be written in terms of objects that have to do with weak decays. So they're very essentially scale invariant. And then you have this isosinglet component. This is the quark helicity. And that's a function of scale. So that's sigma Q squared. And so in terms of the operator of interest, it's the isosinglet axial vector current. So psi bar gamma mu gamma phi psi in polarized proton. Okay, so that's what this sigma is. Now, this is where it gets interesting for this audience, because this is, of course, nothing but the current that satisfies the anomaly equation, as we discussed this morning and earlier in the conference, the workshop. And this current is, of course, not conserved, so d mu J 5 is 2NF times the divergence of the Chern-Simons current, which is nothing but FF dual E dot B. And then there's a piece that's proportional to the quark masses, summed over all flavors, times this pseudoscalar combination bilinear of quarks. So for the rest of this talk, I'm going to work in the chiral limit where I can ignore this term here. And that's a very important simplification, which has very significant consequences if you turn on quark masses. But my claim is that it doesn't fundamentally change the physics, even though it does bring in very interesting elements in understanding inferred dynamics, what's going on. So any questions?
You might have said, Brian at states, what is P and S standing for?
So this is the momentum. So this is the momentum of proton. This is spin. Okay. Or momentum spin. Okay. So now I'm going to talk about how one thinks about this problem in the borderline formalism, and then I'm going to come back to the actual problem of spin. And so this borderline formalism, for those who are not familiar with it, I'm going to discuss it. It's equivalent to the string amplitude forms of Bernoulli-Kosover, which has been used to compute perturbative amplitudes very efficiently. And it's very nice because it provides a first quantized intuition of perturbative QCD or sort of any theory, gauge theory in particular, I mean, in general. And in fact, if you're interested, just to advertise, we have a recent paper or a set of recent papers where we show that we can use this formalism to do an all-order first quantized reformulation QED and address things like invariant safety of the S matrix and so on in this formalism. It's a very powerful framework to study such questions. But they're a little bit orthogonal to this talk, but perhaps connected to the first talk this morning. So also you heard in the first talk this morning about the ABJ anomaly. So it's sometimes called the triangle anomaly. So if you compute the axial vector current, you can show that this is nothing. This can be written in this form here, the triangle anomaly. If you compute this, that's proportional to a vector LK divided by L squared, okay, times the integral over the momenta K2 and K4 of these two gluons that are going to the triangle, times f of dual, and where L is nothing but the sum of the four momenta of these two gluons that are entering the triangle, and essentially L squared is the Mandelstam T variable. Okay, so if you think of a proton that's coming in, which has momentum p, and the outgoing proton is momentum p prime, L is p minus p prime. Okay, so it's the Mandelstam T variable, and so you see that when you compute this triangle, you get this famous pole. Okay, now a remarkable thing is that this object is one loop exact. So if you dress this with all sorts of gluons, then that's robust. This triangle structure is universal to high orders, even though this is just a one loop computation. And all the information, the scale dependence of this object comes in the renormalization of this axial vector curve. And so in general, you can think about the anomaly is as arising from the non-invariant. Sorry, I think series as from the non-invariance of the path integral measure of chiral rotations. And you can write this in terms of Wess-Zumino action by in the following way. You can sort of add arbitrary axial vectors, vector, theta terms, scalar and pseudoscalar sources and fields. And by taking functional derivatives of these, you can write down the anomaly equation as a functional equation. And these are nothing but the anomalous functional Ward identities. And so here's an example of topology as being really fundamental to particle physics. So what I've shown here is the anomaly contribution to pi naught to gamma. So pi naught can decay to 2 photons. And what's shown here, I'm sorry if it's not clear. So these are experimental data for this process as a function of time. Okay, so this is data from the 1960s going out to say 2012 or so. And this is the prediction from just the one loop anomaly calculation. That's a solid red line. And this is one place where theory has been far ahead of experiment. See that the experimental data sort of get better and better, and they converge to this theory result here. And the dashed line as shown is all the higher order chiral corrections to this one loop result by Adler. In fact, so this is really a striking illustration of the topology of the QCD vacuum in this process here. In fact, in the chiral limit, without the anomaly, the pi naught decay. Okay. And for finite quark masses, if you just did chiral perturbation theory without including the anomaly, that would give a lifetime 1,000 times greater than that what's measured in the experiment. So the fact that the pi naught decays and you measure its rate tells you the existence of topology in nature.
There's also a negative result which tells you the same thing, which is that there's no eta prime, no light eta prime.
There's no light
eta prime.
Okay, but that's a more theory, I mean, okay,
Well,
well,
the absence of the anomaly, they might do fine, right?
yeah, agree. In fact, that's what that's what I'm going to be talking about. Yeah.
Okay, so
But this is a very high precision experiment. Okay, so you.
What is the last, you said that y-axis the time, so what is the most recent?
I think this was like 2012 or so.
Okay,
But this is from a review in 2015. That might be better.
Yeah, so they in fact, I think there are experiments at Jefferson Lab that are really trying to nail this down to really see whether you can distinguish, you can really look for the, the impact of the chiral corrections on relative to this one result. Okay, so returning to the Wörl-line formalism. So what do you do? Here's a fermionic action, right, in terms of direct fields. And now imagine that these are coupled to scalar, pseudoscalar, vector, and axial vector fields in general, where D is the is a covariant derivative now in the presence of these scalar, pseudoscalar, vector, and axial vector fields. Now you can compute the one loop effective action of these fermions in the presence of these fields. So that's just a log of the determinant of the Dirac operator. And this has real and imaginary parts. So the real part is nothing but a log of d dagger d. So that's manifestly real. While the imaginary part is the argument of this term d squared. And so we know that the entire dynamics of the anomaly comes from this imaginary part of the fermion, the one loop fermion determinant. So the phase of the direction.
so Euclidean.
This is all Euclidean. And so in fact, there's a beautiful, wait, before I go there, so you can write down the real part, which is the log of d dagger d. You can write this in a heat kernel representation. So you can write down the log of the determinant as trace of log, and then you can use Schwinger's trick and sandwich this log d dagger d. You could sandwich d dagger d in between fermionic and bosonic coherent states, and then rewrite this real part of the effective action as a path integral or point-like bosonic and fermionic fields as a function of which are Wörl lines in proper time. So these are 0 + 1 dimensional objects, and this effective action can be expressed in terms of trace exponent of this Wörl line Lagrangian, which is that of these point-like bosonic and fermionic fields. So these are the kinetic terms. And this is what you would interpret as the Wilson line. So this x dot times the gauge field times plus minus the axial vector field. And this is a spin precession term. And so this is the complete rewriting of the one loop fermion determinant in terms of these bosonic and Grassmann Wörl lines.
So epsilon here is.
And that's the ion bond. And so that's actually imposes the energy momentum constraint of these Wörl lines. So you can think of that as a Lagrange multiplier in general.
Here was on the what of mu in here, mu is power,
Sorry,
mu, the F mu.
oh, that's the gauge field.
Yeah, right, but
So that's F mu nu as a functional A. So this is vector and axial. So A plus minus B. So this is vector and axial vector fields here.
yeah, I mean, that's subscript, like a mu is just power and,
So these are just Lorentz indices.
yeah, right, and power.
Because you said it's 0 + 1 dimension.
Yeah.
Oh, no. So right. So this is now So these are. But I say these are just functions of proper time, but they are multi-components. Okay, so the size, what's that?
The target space were
Yeah.
mu and mu or permanent.
Yeah, so these are so size, the size go from 1 to 4, okay, so they couple to Sorry. Yeah. And so that's a real part of the effective action. And so there's a remarkable observation by De Hooker and Gagne that the imaginary part, which is the phase of the determinant, okay, can also be expressed as a Worldline Lagrangian of 0+1 bosonic, so coordinate and Grassmann fields. And the only difference, so it has a very similar Worldline Lagrangian to what I wrote in the previous slide, except is that you have to introduce an interpolating parameter alpha, which you integrate over, which manifestly breaks chiral symmetry, global chiral symmetry, and where for -1 you have left-handed, and for +1 you have right-handed chiral fermions. And also you have periodic boundary conditions, okay, for these psi and for both the fermionic and the bosonic Grassmannian fields. And this trace is essentially the Jacobian for the zero modes that this for this Worldline Lagrangian, which is multiplied by some G parity factor, okay, which I won't go into.
So this one only reproduces the anomaly and that's it, nothing else. Is there something else in this imaginary part?
Well, I mean, so this is so in principle, this is the I mean, this is just writing down the Dirac Lagrangian completely in sort of arbitrary external scalar, pseudoscalar, vector, and axial vector fields. And this is a very general formulation. And so in principle, you can do, say, recombinant expansion in these four orders. So it has so for instance, you can derive, as I will discuss, Venugopalan terms from this general form of the interaction. In fact, that's where I'll be going. So but before I go there, so thank you for the question. So before I go there, let's just look at the triangle in this framework, and it provides you perhaps the simplest derivation of the triangle anomaly. So this is the one with effective action, as I mentioned in the Worldline framework. So these are again bosonic and Grassmannian point-like objects. And then this is the Worldline action. So here's the Wilson line term. So it's x dot times a mu. Here the sprint precession term. This is psi mu of mu nu. And now if you take the terms from the measure, from the imaginary part, and you can re-exponentiate that in terms of these axial vector couplings here. So if you had no axial vector field, these would just be zero. But what they do is they introduce these additional terms. And now if you take the functional derivative of this one with effective action with respect to this axial vector field and set it equal to zero, that reproduces the anomaly. Okay. And that's just this L mu over L squared, the integral over all these K2, K4, FF dual. So this is a very simple heat kernel sort of regularization of the fermion determinant, which gives you straightforwardly the ABJ anomaly.
So, Roger, the question: how should I think of the overall integral over T?
Overall integral.
Over T, the first integral.
Okay. Yeah. So this is a proper time parameter, right? So it's yeah. So this is dt over T integral. So it's just so you can do this explicitly.
So I should think of that these particles as they're propagating for some proper time T.
Right.
You're something where all possible proper times.
Right. So you can rewrite this in terms of the integral over all momenta, for example, or four momenta. And so this this has also UV and IR contributions as well. Right? So for small t or large t.
A very minor comment. This is just a continuum version of the lattice hopping expansion. That matters. You can think of it that way.
Can I ask a question?
Yeah.
So when having the ABJ anomaly, so we have an option whether we keep vector-like symmetry or axial symmetry, and importing the vector-like if it manifests, we obtain anomaly for axial. And where do we see that kind of choice in?
Wait, I'm not sure I understood your question. So so in the direct determinant introducing this explicit axial vector term, right? So that gives me an imaginary part of the effective action,
I see.
and that's this trace. So it's basically the trace of gamma 5 term that comes in, which you can then sort of re-exponentiate to this form here to linear order in A5, because that's all you care about.
I see.
So this is like an external A5 background field that I'm introducing.
And so
It's not dynamical
in
A5.
in this expression,
Yeah.
vector part of gain invariant vector part is already manifest and only possibility to break axial body.
That's right. So this is like an external background field so that I'm introducing and then I'm turning it off.
Thank you.
Right. So that's yeah. So I'm. And so now returning to this problem that I mentioned is that the issue is that if I'm computing J mu 5, so this is the object that I mentioned is the quark helicity, right? And what you see is that the quark helicity has this contribution which diverges in the forward limit. So if I think of some scattering, so I have some incoming proton, polarized proton momentum P and outgoing one momentum P prime. And they have a relative momentum, forward momentum, that's this L. In the forward limit, right? So if I were to take the imaginary part of the forward cross section, forward amplitude, I have to take L going to 0, and you see that this diverges, right? And so this is a genuine pole, sometimes called the Kogan-Susskind pole. And the question is, how do we address, how do we treat this pole? Okay. And it turns out that this is actually now treated very well in the literature of perturbative QCD, how this is done. In fact, there's a huge debate in the literature shortly after the spin crisis became a crisis, and there were people who sort of argued that you could actually interpret this as a local operator, really ignoring this fact that there's this divergence as L squared goes to 0. So there were calculations of the quark helicity, which were not done off forward. Because they were not done off forward and made kinematic approximations like collinear and high energy approximations, they missed completely the fact that there is this pole here that one has to handle. And this was something that was actually noted by Jaffe and Manhar in the classic paper. And so these authors that he's referring to are Collins, Mueller, and Karlitz, and also Alberli and Ross. So really well-known people. But they claim that what they did is not quite right. And they said that if you compute this object is really the quark helicity, they're saying if you believe them, and this is a local probe, all right, then this would be protected with the infrared problems, which is what these 1/L squared poles, and the calculation would be reliable. However, we believe that there's strong arguments that triangle is not local in the sense required, so the triangle operator is intrinsically non-local, and it's therefore not necessarily protected from infrared effects, in particular those that give eta prime mass. And so this is precisely the statement that somehow this resolution of the quark helicity, why you get this divergent pole, is somehow deeply related to physics of the eta prime. And so the spin problem is deeply tied to the UA1 problem in QCD. So that's the one takeaway. And this was actually pointed out by Veneziano, and Son is very familiar with this metal that he's wearing. It's a direct metal. And so even though this was pointed out by Veneziano, his work was almost entirely ignored. Okay. So you can actually find books on the spin of the proton where you see almost no reference to his work. And so one of the subtexts of my talk is that he was absolutely right. And what we do is actually recover Veneziano's results in a different way, which also allows us to go a little bit further. So in essence, what you find is that if you look at the imaginary part of the Whirlwind effective action that I wrote down for you, and you work it out, perturbably, do an expansion in these scalar, pseudoscalar vector and axial vector fields, you find that from the phase of the determinant in the imaginary part, you actually recover Venugopalan terms, in particular one that corresponds to the coupling of a pseudoscalar, which I'll argue is a primordial eta prime, which couples to FF dual. So occasionally I'll write omega, capital omega as FF dual, is to represent FF dual. So it's a topological charge density. And F eta bar is the eta bar decay constant. So if I sandwich the axial vector current between the vacuum and the eta bar state, that's what F eta bar is. And so within this wordline formalism, we were able to explicitly compute this term. And to the best of our knowledge, we haven't seen this anywhere else in the literature. The only place we found it was in a beautiful paper by Kaiser and Leutwiler, where they just state this result. They don't give an explicit derivation. And our expression agrees exactly what they had. And I want to point out that our derivation is exactly analogous to the derivation in this framework of the Venugopalan term that's responsible to apply out to gamma. So we did sort of exactly the same calculation, and you find that there's a term which couples the primordial eta prime to FF dual. And this has very remarkable consequences, which will become apparent shortly. But in fact, essentially what you then get is that you get an axion-like effective action. So you have a kinetic term for this eta bar field. So it's massless. Then you have the theta term, QCD, so that's theta times F dual. And then you have this Venugopalan term, that's eta bar times omega. And you would have the term that's the proportional to the Yang-Mills topological susceptibility. So in other words, if you took the second derivative of this action with respect to theta, that would just be the topological susceptibility of Yang-Mills. Now, since theta is not dynamical, you can get rid of it from the equations of motion. So in the chiral limit, we know that there's no theta problem, right? So you can just do a shift, get rid of it. And then what you're left with is just an axion-like effective action. So there's a kinetic term, this is Venugopalan term. And then there's a term which comes from this topological susceptibility, which is omega squared over 2 chi. Now I can do again a simple shift of this eta bar, and you can replace this omega by some field G. And what you get then is nothing but the equation for the eta prime. So so you can replace a massless eta bar by a massive eta prime, where this eta prime is the usual eta prime mass given by the Wittmann-Zano formula. So I'll come to sort of an explicit discussion of that in a minute. And then there's a non-propagating U-ball that just decouples from the spectrum. So the essence of the physics in the chiral limit is that of an axion-like effective action. In other words, alternatively, there is an axion in QCD in the chiral limit, and that's nothing but the eta prime, which represented in terms of this.
Just check my understanding. So omega is FF dual.
Yes.
So then the last term in the second equation from the top is dimension 8.
Well, no. So remember that this is the topological susceptibility. So it's omega correlator.
It's a number.
Fourier transform.
It's a number.
Fourier transform.
It's a number. Yeah. So as an operator, it's dimension. Okay, that's fine.
Yeah. So now, if you were to do instanton physics, then you would say, well, this topological susceptibility Yang-Mills is saturated by classical configurations, and there'd be discussions of spin in the language of instantons. But this is a much more general formulation in terms of these Venugopalan terms. Okay. And so what I'm going to now argue to you is that as a result of all of this axion dynamics, you get a very interesting kind of Goldberg-Tremont relation. So let's again look at this quark helicity. So as I mentioned, it's the isosinglet axial vector current that's sandwiched between momentum, outgoing momentum P prime and incoming momentum P of a polarized proton. Right? And so you can write this in terms of spinors most generally as an axial vector form factor. So this is gamma mu gamma phi, an axial vector form factor, which is a function of the momentum transfer L squared. And then there's a pseudoscalar term. Okay. Now, this term here can be written diagrammatically as a direct coupling, okay, of J-mu5 to a polarized proton. So if you have a direct insertion of a J-mu5 operator on a polarized proton, that would be this axial vector form factor. And the pseudoscalar form factor corresponds to the following contributions. So one is the anomaly contribution that I talked about. So if you remember that J-mu5 can be written as L mu over L squared times omega, which is the topological charge density. And this can be represented most generally in this form here, where this is a susceptibility. So you have omega, omega. Okay, so you have J-mu5 that couples to omega, and then there's a correlator omega, omega. That's a topological susceptibility. But that in general can interact with this eta bar field, right? So there's an eta bar omega coupling, so there can be this exchange of an eta bar to T channel. And then they can also be then a direct coupling of the topological susceptibility to the proton, but in the Carr limit, I'll argue that goes to 0. So now let's consider the direct axial vector coupling. Now, strictly speaking, in the forward limit, since there's no pole in the pseudoscalar form factors have no poles, I mean, they're smooth, right? Like this is the physical quantity. So in the limit L going to 0, this object is well defined. And so if I take the forward limit, then all the sum of these other pseudoscalar diagrams here, the sum of these three must be 0. And so the expectation value of the isosinglet axial vector current is nothing but the axial vector form factor multiplied by the spin 4 vector. Okay. So another way of saying it is that the helicity of the proton, which is sigma, is just twice its axial vector charge. So that just follows from this expression here. So now if you look at, let's look at this contribution here, where this gray blob represents the coupling of J-mu5 to the probe. So this is the decay of this J-mu5 to these two photons. And then I have this T-channel exchange of this primordial eta prime, which is eta bar field that I mentioned here, which then couples to the proton. And so if I write down this matrix element explicitly for this term here, so I have a coupling, which I call G eta naught NN, which is this coupling of this eta field to the nucleon. I have a spinor U bar gamma phi U, so that's a pseudoscalar matrix element here of the proton. And then there's this massless field, which is given by 1 over L squared. So it's that's the propagator. And then there's the decay of this object to two photons that's given by this eta bar decay constant times L mu. And so similarly, these terms here that I mentioned, this is the anomaly term that I talked about. This term here, that's what I call C. That term here is nothing but just the expectation value of forward of FF dual multiplied by L mu over L squared. And so now if I take this general expression that I had here, right, and then I contract that with L mu and use the Dirac equation, I can show that this axial vector charge can be written in terms of the eta bar decay constant times coupling of this eta to the nucleon. And so this is nothing but the Goldberger-Triemann relation for the isosinglet axial vector. It relates, it's a fundamental relation that relates the physics of what goes on in the axial vector sector to that of the pseudoscalar sector. And it's a fundamental property of the low energy dynamics of the flavor non-net sector of the low energy dynamics of Carl dynamics. So this is a very important result. And so I think I should just probably well, let me go through this a little bit. Now it turns out that there's also an interesting fundamental relation between this eta bar exchange, which then decays to 2 photons, and this anomaly contribution that I've shown here with the topological susceptibility. Okay. So let me just sort of look into this bubble that I wrote here. And this bubble is the QCD topological susceptibility. It's the correlator of omega omega. That's what these two black blobs denote. It's correlator of two spatial positions of omega omega, the Fourier transform of that. So this can be expanded in a 1/n expansion in terms of the Yang-Mills topological susceptibility times the coupling of the Yang-Mills to this eta bar field. So that's the Vesuvian-Witten coupling. There's an exchange of the eta bar, and then you have another such Yang-Mills bubble here. And so since the denominator of the Vesuvian-Witten term is 1/√n, this is a 1/n correction. And so you can do a resummation of all 1/n such n 1/n corrections here. And so thus from the Yang-Mills topological susceptibility, you can regenerate the QCD topological susceptibility, which, as I mentioned, is nothing but the Fourier transform of the correlator of the FF dual. And so you find when you do this resummation that the topological susceptibility of QCD is nothing but, so you do this resummation, you can rewrite this as L squared times 1/L² minus n eta prime squared. So you shift the pole that was there previously. So there was a 1/L² pole, you shifted by m eta prime, where m eta prime is given by nothing but the Witten-Van-Zanoff. So you see the Witten-Van-Zanoff form just kind of drops out this framework here. And of course, in the large n limit, this goes to 0, right? So for any finite n, m eta prime is non-zero. And the reason why this is a large number is because the Yang-Mills topological susceptibility is very large. So from the lattice, we know that's on the order of 198 to the fourth. And so for finite n equal to 3, this is a very large number here. But it's in the limit of large n, this goes to 0 smoothly. So what this tells you is that even though the Yang-Mills topological susceptibility is very large, the QCD topological susceptibility is very small, because you can see when I take the limit L² going to 0, this object goes to 0. Okay, so in the chiral limit, the QCD topological susceptibility is 0. So what you're just seeing is how you can topologically generate a mass greater than that of the proton mass. So the eta prime has a mass which is 957 MeV, so it's larger than the proton mass, and it's entirely due to topology. Okay, so that's sort of going to your point earlier. And so you can actually, so I don't want to go through this in detail, so you can also begin work through these different diagrams. And you can show that this object here, the eta bar decay constant, can be written as a vacuum correlator of the topological charge density in this eta field. And if you use this expansion that I mentioned here, you can write down this correlator as nothing but the QCD topological susceptibility, that's this bubble here, times this 1/L² propagator. But as I mentioned, the chiral limit, this object is 0. So if I do a Taylor expansion, I find that the eta bar decay constant can be written as the slope of the topological susceptibility at 0. So putting everything together, I find that the quark helicity, so that's J-mu5 in the proton, so that's sigma here, is nothing but the square root, it's proportional to the square root of the QCD topological susceptibility in the forward limit. Am I going over this? Yeah. So by the way, so this is the result that was obtained by Venugopalan. Okay, so what Venugopalan showed is that the quark helicity is nothing but the square root of the QCD topological susceptibility in the forward limit. Okay. So this tells you that the quark helicity is entirely determined by the topological susceptibility of the QCD vacuum. So I should probably end here, and I'm way over, right? Yes. Yeah. Okay, so thank you, Sure. We should give you a warning. Okay.
I'm sorry, it's my fault.
Okay. So anyway, so this is kind of one of the punchlines of my talk. So let me just and this is consistent with data and so on. So this is something And so I just wanted to say that when you look at the G1 structure function, I'm just going to splash you the results very quickly. I'm going to, and what you can see is that this G1 is then proportional to, it's actually given by the sphaleron transition rate. So what you can have is in addition to, when you have, so as I mentioned, the quark helicity is proportional to the topological susceptibility. But now if you go to very high energies, that's like having a high temperature inside the proton, and you can have these kinds of over the barrier transitions between different vacua. And what that does is that results in, on a drag on this axion, which is the eta prime, in sort of in this background field of all these dense gluons. And this drag coefficient is nothing but the sphaleron transition rate. So the bottom line is that if you measure this G1 polarized structure function at small x that I was talking about, it is very rapidly quenched as you go to small x. And so from this quenching, you can really extract the principal information on the sphaleron transition rate. And so there's a very simple picture of this. So imagine that you have a quark with a certain helicity going through this blob, this object here, which is a proton with all these gauge configurations. And each of these blobs corresponds to a size of the order of the string tension of these objects here. So that's the spatial Wilson loop that gives you the string tension. And so the sphaleron transition rate is proportional to the string tension squared. And so you have this blob that's carried here. And so the helicity flips of these quarks is given by the amount of topological charge that's carried by these objects. And that's given, the root mean squared of that is given by the sphaleron transition rate. So as you go to higher and higher energies, the sphaleron transition rate is greater. Okay, the number of, so the root mean squared topological charge is greater. And so that creates more and more helicity flips. That's what leads to a rapid quenching of the proton spin. So as you go to higher energies, you see that you have more and more such of these blobs, which carry more and more topological charge. And so you see a complete sort of, you see a complete quenching of the, you see lots of flips, the helicity flips of the quarks as they go through this medium. And that's really what's responsible for this rapid quenching of the structure function. Anyway, thank you for your attention. Sorry for being on time.
We have time for one or two short questions before we go to break. I didn't mean to scare, not to ask a question.
So you said sphaleron contribution is effective in high temperature?
So sorry?
Did you say that sphaleron contribution is effective at high temperature?
Yeah, so what happens is that as you go to higher and higher energies, what you're probing inside the protons live in more and more excited configurations containing larger and larger amounts of gluons. And effectively these gluons are very closely packed, and so they have a very large intrinsic momentum, if you like, which you can interpret in terms of temperature.
High energy.
Sorry? Yes. Yes.
But naively I expect that high energy condition because of the asymptotic freedom, so the catalytic QCD contribution
So good question. So there's two things going on. Is that so? There's high resolutions, which gives you asymptotic freedom, but then if you have high boosts, you produce more and more gluons. So this is so imagine you're a quark, you have some resolution, right? And because you have a very fine resolution, you are indeed seeing individual gluons, as asymptotic freedom tell you. But then as the proton is boosted towards you more and more, you see more and more gluons being produced. There's a lot of Bremsstrahlung. So essentially in your resolution, you see a very large number of these gluons, and at some point they're so closely packed, you can't really distinguish between them. So it's a weak coupling, but very high, strong field regime that you're probing.
Thank you.
Okay.